So, good evening, everyone. My name is Yossi Moalem. By the way, raise of hands. Who was here on the first conference in 2019? Anyone? Okay, quite a few. So, if you yeah, so if you remember, there were two. There was a talk by Nimrod Sapir and about HFT, and I really wanted to attend this talk. And there was a slight problem about it that I couldn't attend because I gave a talk at exactly the same time. So obviously I could have looked at YouTube and see it, but that would be like the most obvious thing to do. It's kind of boring. So instead I just joined Nimrod in QSpark, and then Nimrod was promoted to chief architect, and I replaced him as the VP R&D. So that's a very convoluted and long way to say, good evening, my name is Yossi Moalem, and I'm the VP R&D of QSpark.
Hello, my name is Assaf Wolfhart. I'm a software developer at QSpark.
I think it won't surprise you very much to hear that QSpark is an HFT company. I mean, anyone is surprised to hear this? I very much doubt. What we do in HFT is basically HFT, or high frequency trading, is a branch of algo trading, and what we do is we specialize in buying and selling large amount of stocks, holding them for very short amount of time, and hoping to make money from this. When I'm talking about very short period of time, it's normally around minutes, seconds, and sometimes even sub-seconds. And I think that the thing that characterizes the most HFT is that we give a very great deal about performance in general and low latency in particular. And the question is, why? Why do you care so much about low latency? So what we actually do is we have our servers located in the American Stock Exchange data centers, and we consume all of their data feeds, meaning we get notification each and every time someone wants to buy or sell a certain stock. And then we look and we try to locate or to spot some attractive deals. And when we do it, we execute an order asking to buy or sell this stock. Now, unfortunately, our competitors are consuming the same data feeds and are trying to locate the same deals, and we simply need to be faster than them because we either faster than them and then we get a deal, or we are not and then we get nothing. There's no second place. Now, just to put everything in sort of a time frame, from the moment that we first get the notification about the deal, about a trade that happened in the stock exchange, till the moment that we send the order, if we find it to be attractive, it's something like 3, 4, maybe 5 microseconds. So obviously, reducing even few nanos can have a dramatic effect on our overall performance. And that's make it, in my opinion, very exciting. It's important to know that our servers are dedicated servers that are there only for trading. They should not do anything else. What we will do in the next, a bit less than an hour now, is guide you through some of the most basic techniques and challenges that we face in our day-to-day work. But before we'll do that, I would like to give you a very short overview on our overall architecture. Assaf.
All right, so our high-level architecture looks like this. We basically read data from the network buffer, parse it, and apply some filters. Then the data gets updated in internal data structures and gets forwarded to the trading logic. The trading logic handles thousands of events per second. Only some of them are getting to the orders which get sent to the market later. But before that happens, we apply some risk checks. And those checks are important to make sure that things like price and quantity are within appropriate ranges. The history of HFT has its own cases where orders in millions of hundreds of millions of dollars were submitted to the markets just because they lack those risk checks, which is why those are so important. And if you look at that as a very sad thing for that company, please remember that somebody got rich. So after we apply risk checks, our orders get sent to the market, basically. And apart from our real-time threads, there are also administrative threads which handle logging, monitoring, connection management, and other administrative tasks.
Well, Assaf, you're talking about taking very high performance and running everything as fast as possible, but then you have all these admin threads that are practically competing on the same resources. So what actually stops the scheduler from, just before you send the event to the stock exchange, decides, now it's really time to flash the logger or do any monitoring or something like this, and then all your latency goes down the drain?
All right, so in order to avoid any context switches, we divide our threads into 3 tiers. The first would be the real-time tier, the second, the administrative threads tier, and the last are the system processes. And I want to mention that our trading systems are designed basically for trading. They don't do anything else but those trading. So our decisions are a little less standard. So let's consider, for an example, an 8-cores machine, which runs 5 real-time threads. Those would be the 5 cores on the right side of this slide. And we isolate each of those core, which make each core run exactly one dedicated thread. And it wouldn't run anything beside that. We use isol CPU in order to perform that. It's a Linux feature, which is available in most distributions. And we make sure our threads are spinning and never stop their execution the whole time. Apart from the real-time threads, we have the administrative threads and the system threads. And we have 2 possible configurations for those. The first one would be that we would use the very same isolation for them, which means each of those threads would be isolated to a group of cores, and the scheduler would start one of them, would start the thread in one of those cores. The scheduler isn't very keen at moving out threads out of their cores because we've instructed it not to do so using isol CPU. The last core would account for the system threads, which run everything else the system runs, such as SSH sessions, anything else somebody is going to run on that system. The second possible solution is to have the administrative threads and the system threads share the 3 last cores equally, and that all those cores would remain non-isolated.
So how do you choose between them? I mean, you showed 2 configuration. How do you choose which one to use?
Right, so in a matter of fact, it's a trade-off of utilization versus safety. And what do I mean by that? If we would like to make sure that our threads are getting execution time, we would choose the second solution because it allows any thread to run on any core. And if there is a core available, the scheduler would make sure that your thread will get executed. But that has a weakness inside it, because if some user of that system, which is a dedicated trading system, would try to run on that system something which is CPU intensive, it might steal CPU time from the administrative thread, which is going to compromise our trading platform, our trading process. So it's a matter of trade-off between those 2.
The scheduler is definitely not the only part of the kernel that you try to bypass. As a matter of fact, we try to bypass as much as possible from the kernel. I think it won't come as a great surprise to hear that in our real-time threads, we avoid any system calls. That's mean that, for example, we can't use dynamic memory allocation. We use static memory pools, and one of the administrative threads simply scans those pools. And when the amount of free blocks that we have goes beneath a certain watermark, this administrative thread simply allocates more memory and splice it to the real-time thread. So making sure that the real-time thread always gets enough resources for it to operate properly. Another thing that we bypass the kernel is the networking. The kernel is simply too slow in processing it. If you let the kernel process our TCP IP stack, it would take something like 4,000 nanoseconds, which is eternity in our world. So what else can we do? Do we write the whole TCP IP stack in user space?
That's an interesting idea. What we actually do is use solar flare cards. Solar flare cards are provided by Xilinx. They have three possible tiers or implementations which you could use in order to improve the performance of your packet processing. The first one would be onload. Onload is a host for your process, which effectively you run your process with onload, and it hooks to the kernel code, and functions such as connect, send, and receive are transmitted immediately to the onload kernel. The second layer they provide is named TCP Direct. It requires a lot more efforts in order to implement it. It requires far more customization in order to use it, and it allows direct access to the card, to its API, and environmental changes, and it's pretty hard to make it work in your favor. The last and fastest, best tier they provide is named EFVI, which stands for Ether Fabric Virtual Interface. It stands for, it allows much lower level API, allowing direct access to the queues, direct access to the NIC, to the network interface, and it also comes with the responsibility of managing the packet processing and everything which is related to networking. It is designed for ultra-low latency industries like ours.
It's important to notice that those optimization and that we just described here has to do a lot more with the latency and very little to do with the overall throughput of our system. And that's something that's very characteristic of all the optimizations that we run. We care a lot more about latency and very little about throughput.
Aren't those two somewhat related, Yossi?
They're related, but they're not one-to-one connected. If I wanted to increase the throughput, I can, for example, use multi-threading, and then even if each thread takes more time, the throughput will probably increase. But honestly speaking, just talking about throughput in our system is a bit absurd. What we have is we have a stream of data, a stream of messages, and we need to process it, process each one of the messages. And as long as we manage to process it in time, that's good enough for us. The time that we measure is between starting the processing or getting the message and ending the process. And even if we have time that between ending and processing one message and we didn't yet get the next one, we won't try to use something else increasing the overall throughput because we don't care about it. What we care is the latency. But to be honest, this is also not totally correct because let's say that the first event we filtered out, it's not a stock that we are interested in. The second event, we looked at it and we decided, no, it's not a very, very good deal. Third one, yes, it's a good deal. We definitely want to try to issue an execution order and get this deal. And then we got another one that's not important. All those events that we did not issue an execution event for, we simply don't care about. The only single event that we care about is this event that we do send an execution order for because that's the only thing that actually generates money for us. And this is a very important concept, so let's delve it a bit deeper into that. Let's say that I have a basic implementation that the non-important events, those events that that did not generate an execution event, takes us 2 microseconds to process. And the event that we did generate execution order for takes us 5 microseconds. If for every 1,000 non-important event, non-good event, we get one event that we send an order for, the overall time that we'll spend will be 2,005 microseconds. If we'll change the implementation a bit, and we will get the events that are not important for us will increase by 50% to 3 microseconds. But the one single event that we are interested in will decrease from 5 to 4 microseconds. Overall, we spent a lot more. We spend now 3,000 microseconds. But this is good for us because the one event that we are interested in will get to the stock exchange 1 full microseconds earlier. And that could be the difference between having a deal and not having a deal. And that's a very important concept for us. We are optimizing for the very rare case. Now, I think one thing that we noticed while we profiled the application is that the first stages of the parsing and filtering runs much, much faster than the later stages of the risk check and constructing the execution order. And I think that in this audience, it won't come as a great surprise for you that the reason is caching. The first stages run constantly on every event. The later event run once in a blue moon. But that's actually a bit tragic as far as we're concerned because that's the hardware responsibility and there is not much we can do in order to get all of it hot in the cache. So we're kind of stuck, aren't we, Assaf?
So actually there is some practice which we are using in order to make sure that we can have the right side of the slide run a bit faster, and it's named cache warming. Cache warming is a technique which we are using in order to send every 1,000 events or maybe 100 events. It's something in which we can configure to make sure that some dummy orders or cache warming orders are sent to the market. So we will use cache warming orders in order to make sure that that part in the cache.
It's kind of silly. I mean, in my book, when you want to increase latency, you do less operations, not more. Here you're just sending an order just for the fun of it?
Right. So yes, we are wasting some of the time, but the fact is, it's time wasted on events which we are not extremely interested on. We are interested in making sure that the events that are important for us happens as fast as possible. And if that means that we will spend extra time at some other places, we are fine with that.
So it's actually what we just described, that we taking longer on the non-important event, but reducing the time that it will take us to execute the important event, right?
That's correct.
But there's still something that a bit bothers me. Obviously, when you send an event, you don't just send it and forget about it. You have to update your internal state in order to know what's your current exposure. So obviously, you have to ask, is it a cache warming event or is it not? So aren't you simply warming the non-important branches, and all the branches that are for the real events may still be cold?
So an important practice in cache warming is to make sure that your cache warming code isn't aware it is running any cache warming code or contains any branches about cache warming. And we'll see in a simple example and here it is. We have a simple counter of total number of orders. This is how a non-cache warming code would look like. So after it is adapted, we will choose either of those two. The first one would be that we will have the right side of this equation will result with either 0 or 1, and we will add it to the total number of orders. So that part of the total number of orders would get incremented anyway by either 0 or 1, independent of the fact if it is a cache warming order or not. The second solution is to have an array of 2 counters, which we will increment the relevant counter, and this is also a branchless code.
Quite cool, must say. If you're talking about not caring about the non-important event, the events that do not generate execution order, we can talk also about the risk checking. The risk check is constructed of a series of checks, and they all need to pass in order for us to send the order. If one of them fails, then the order is too risky and we do not want to send it. And that's a very rare case that the risk check fails. So the simplest way, the most trivial way to write it is like this. We simply call it, and each one of the checks return a return code. And if one of them, if it fails, we simply immediately return. Another way to implement it would be as demonstrated here. And as you can imagine, each one of the checks throws an exception in case it fails. And we simply catch the exception.
Aren't those exceptions on this right part of the slide a bit slower compared to the risk check?
They are a lot slower, but exceptions are very slow when you throw an exception. When you throw an exception, that's it. Your application performance goes down the drain. But if you do not throw an exception, that's the easiest and fastest way to signal that everything was fine. It's it's faster than even checking the error code, because you practically do nothing when exception is not thrown.
Well, I remember a saying that says nothing is an optimization unless it is measured, and we do have some measurement of that, which shows quite the opposite.
Okay, this thing we measured, and yes, we do, that's the correct result, and there is one error here. Anyone wants to guess what the error is? Just hit, it's not that the legend is wrong. Okay, what we actually measured here is the time that it takes for the risk check to complete. All the time. So it includes the events that are important for us, that pass the risk check, which is the common case, but also the events that did not pass the risk checks. Those events did generate an exception, and as we said, when you throw an exception, that's extremely, extremely slow, but we don't care about it, because those events we will not send an execution order for. So we are happy to pay this in order to get slightly better result in the case that we did pass the exception. If we remove this from the measurements, that's what we see. We are a bit faster without checking the error codes and counting on exceptions. What I want you to remember from this, if you can take 3 things from this talk, that should be the second one. When you measure, micro-benchmarking is good. It's excellent. We love it. But make sure that you understand the results. And I'm not saying by any means that you should bend the results to fit what you believe. No. But make sure if the result does not make sense to you, you're either measuring the wrong thing or you do not understand something. So at the worst, you learn something new. But even more important, test it in your application. Something can look very good on a macro benchmark and then be a pessimism on your application. So do measure it in your application, in your scenarios, and only if when you're checking in your application, it sounds good, then implement it. And now for something completely different, if you do not know the reference, you should definitely watch a lot more Monty Python. I want to talk to you a bit about sharing data between threads, which is something that obviously none of you ever done, but it's something that we do. So let's say that I want to read and write from several threads. That's a very, very simple way to do it. I'm simply writing my data structure with atomic, and it will compile, and everything work well and will be correct.
So it's pretty easy to see that that data structure which you have might contain some hidden locks in it.
Exactly, and that's why every time that we do wrap some data structure with atomic, we should always assert for it being lock-free. Because if there's one thing worse than having a lock is having a hidden lock. Now, unfortunately, if we do need to have this generalization, and if we do need to have many threads read and write the same data, we probably have to have locks, but maybe we can find some relaxations. For example, does the whole data structure needs to be atomic? Let's say that we have a list of stocks, and each stock have its quantity and price. Obviously, each share needs to be atomic, and that can probably be lock-free atomic. But does the whole list needs to be atomic? If it is not, then we can simply break it into substructs that are atomic. It is correct that the whole data structure will not be atomic, but maybe that's acceptable for us. Another thing that we can consider is whether or not we can fail an update or a read and do it later. So the simplest way to do it is just, instead of using lock, use try lock. If we succeed in acquiring the lock, we'll update our data structure, we release the lock and go to the next operation. If we did not, we'll simply go directly to the next operation, but this has a hidden possible cost. Let's say that I did acquire the lock and I'm starting to update my data structure. Another thread comes along and locks this mutex. When I'll try to release it, the kernel will need to inform the other thread that the mutex is now free and it can continue running. And that can be a very costly operation. In this case, we can simply use spin locks. That's the simplest implementation of a working spin lock. As you can see, when we lock, we simply exchange an atomic boolean into true until we succeed. We never go to sleep. And when we try to unlock, we simply set it to false. However, this is very simple, so it's obviously not very good implementation. There are two main problems with it. The first one is the cache consistency protocol has to make sure that whenever someone tries to write, it needs to have the only access to it. So this cache consistency protocol, whether it's messy or something else, will flood the system with messages, and that can decrease our performance. The other possible problem that we have is if we took the lock, other threads may spin for a very long time. So if, for example, we acquire the lock and then we context switched out, the other thread will use all of its time slice simply spinning and won't let anyone else run along. So a better implementation of lock is as follows. We simply try once to exchange and to acquire the lock, because we favor the success path, because lock should most times succeed in locking. But if we fail, instead of trying to acquire it again, we simply read the value of the atomic boolean. And only once we succeed, we try to acquire it again. If we acquire it again, good enough, we break out. If not, we repeat this process again and again. And also, after a few times we read the value and we see that the value means that the lock is taken, we will consider yielding, giving other CPU cores the chance to run. So another thing we need to consider is, are the updates that we want to implement are dependent upon each other, or are they atomic? If, for example, we have price, if we have a set price, I can update the price even if I did not read the latest value. If I have deltas, then obviously they depend upon each other. I will not show how this impacts performance for lack of time. What I do want to discuss is the number of reader and writer threads that we have, and what the runtime thread is actually doing. Is it a reader or a writer? So let's say that we have a reader and a writer and they want to share some data. So instead of pointing directly into the data, they'll point into an atomic pointer pointing to that data. When the reader wants to update this data, it will construct its own data structure with the values that it wants to use and simply swap the pointer to point into the new data. But that leaves a huge memory leak, because who is responsible for clearing up the old version of the data? Now, a very simple solution would be that the reader will set a flag before it starts to read the data, read the data, and then unset the flag. The writer will check if the flag indicates that the data is used. If it's not, it will replace the pointer and release the old data structure. I think that it's very easy to find the race condition here. Say that the writer checks the flag. After it read the flag, the reader sets the flag. The writer that saw that no one is using it will replace the data and will release the old data structure. And when the reader will want to read the data, it will crash because it will read released data, or its undefined behavior actually. So a much better solution would be to meld the data that we want to share, which is the pointer, with the flag into one object. The way to do it is that the reader will swap the pointer with null pointer atomically, holding the old value in its hands. We'll read the data using this pointer, and when it will finish the update, it will restore the old PTR. Now the writer will run a compare and swap loop, and when the value will not be null, it knows that no one is holding the data, so it can swap it and release it quite safely.
But doesn't that case support another reader, or does it?
That's a very good question. If I'll add another reader, then all this solution will not work, because if they will both try to read it together, one of them will get null. So the solution here will probably be to use reference counting, and that introduces further latency, further work that we have to do. First of all, for the incrementing and decrementing of the reference count, and secondly, the reader, that in this case is probably the real-time thread, may be responsible for the distraction of the data, which is something that we definitely do not want, because this distraction can be very costly. So we see here, we normally talk about synchronizing multiple readers, but we see here that even if I'm reading just a reader, not a writer, we just had one reader, it already hinders our performance. So if you said that you should take 3 things from this, let it be the third thing that you take. Premature generalization is the root of all evil. Take any advantage of any relaxation that you can have. Use the most specific data structures and algorithms that you have. If you know that you're only going to have one reader, take advantage of it. Don't use reference counting just because maybe one day you'll need it. You don't need it now, don't pay for it now. Pay for it if and when you'll need it. I would like to discuss now some real case scenario that we actually had in our application of using the wrong data structure.
So just a second, please. Mm-hmm. So up until now, we have been covering optimizing for latency, and I want to cover a case where we need optimization for throughput. So one of our products distributes data to the markets, broad data from the whole US equities market, and it is required both for trading strategies which require that broad data, or for trading strategies which uses very certain order types which require them. I want to emphasize that latency is still very important for us, but whenever there is a trade-off between those two, we would tend to prefer throughput. Here's a general overview of our systems. Our threads read data from the network buffer, and it generally gets pushed into a central queue. And then it's getting popped from another thread and gets processed for further processing. And of course, this box on the right doesn't really represent what is actually happening there, but we would like to focus on that queue. So there are 2 times in the market which are extremely loadish and challenging. Those are known as the open and the close of the markets, happening at 9:30 and 4 a.m. and p.m. Daily, on trading days, on Eastern time. And on those times, the market extremely challenges us by throwing that vast data on us. And slide, please. On those times, the network buffer gets saturated, it gets filled by the data that the markets send us, And it means we are dropping some packets. And that contradicts exactly what we would like to do. We would like to make sure we have all the data from the whole day, from the beginning till the end of it. And we wanted to understand what we can do, because nobody can change how the market behaves. But in order to understand better what we could do, we have started to zoom in this queue and what those functions are doing when it reads data from the network. So we are using vTune, which is a statistical analyzer. It basically shows you where exactly your functions are spending their time, the majority of their time, and are they efficient? Are they doing exactly what you would like them to do? And we saw some exaggerating statistics with 4.4% retiring, which is represented by that slim green line, happens to present our push function, which makes them extremely inefficient. On the other end, on the pop function, there's some better relaxation. It shows as a 15% retiring. And retiring, by the way, means that the CPU is executing your functions, your code, and it doesn't wait for any memory operations, or it doesn't mispredict its branches or anything like that, but just process your code.
Hold on, Assaf, hold on. Are you saying that our implementation of log-free queue is crap?
So it's actually a matter of making sure that we take the right tool for the job, and this is a classic case for that.
When we say log-free queue, it's not a single container like vector or list. It's actually a family of containers. It could be single consumer or multi-consumer, single producer or multi-producer. What do we do when the queue is empty? Do we simply return a sentinel or we return false? What do we do when we want to push when the queue is full? Do we simply overwrite, which is very simple, or do we need to detect it and return false? Also, for some of these combination, what do we favor? Do we favor the readers or do we favor the writers? That can have a dramatic effect on the overall performance. So in this case, it's not that our implementation was good. It's simply that we did not choose the right implementation. We used multi-producer, multi-consumer queue that did not favor the writers, and that was the mistake.
So we wanted to understand if we can do any better, and I was working on this with a colleague of mine named Anna. She couldn't attend today, and she thought we could definitely do better, and together we started to outline how that new queue would look like. So we definitely want to use a single consumer multi-producer queue. We want to make sure that the producers is known at compile time. If that happens to assist us in making everything faster, we want to favor the writers because we want to make sure that the network buffer is kept as empty as we can. And we want to reduce the writers sharing and the readers and writers sharing between threads, and last, to use the best memory ordering functions which we could use. Here's a general overview of how that queue looks like. That big queue is represented by number of sub-queues, which is basically the number of producers which we have. Each thread has its own sub-queue and writes items only to that sub-queue. So they don't actually have any contention between them on the actual cell they are going to write the data to. The only synchronization which they have is the write ID, which gets inserted to the queue along with the item we store. So in this case, we have 4 producers, and if thread 3 happens to insert the first element, it would go to the third sub-queue. Then thread 4 comes, inserted the second element, which would be inserted in the fourth queue, and so on and so forth. And that's for the writer threads. On the other side of this slide, we have the reader thread. reader thread would have to work harder, and that effectively shows how we favor the writers, because they have minimal synchronization, and we try to make them work the minimum which is required. On the other hand, the reader thread is going to loop over all those subqueues and search for the ID it has to consume. So it found the ID 1 on the third queue. Next, it's going to iterate and find the item number 2 on the fourth queue. And I wanted to let you know that that thread is kept under a very tight loop, under a busy loop. So it keeps iterating and getting inserted again and again, trying to pull items from the queue. All right, let's see some code. So here's how our push function look like. We are using thread local storage, and we get the queue index from, and it happens only once per call to that function. And writer threads, of course, call that function a lot. We basically use the relevant cyclic queue, subqueue to push the item to. We forward the item along with the write ID we want to synchronize on. Pushing items into the internal cyclic queues is basically referencing a very specific cell, and which is known to us, and we just want to make sure that that cell is free. It doesn't have any item in it. Then we would reference that cell, move or copy the item, depending on what the item is capable of, and only then we would mark it as consumable. And the ordering of those two instructions is extremely important, because we want to make sure that items are getting read only after they've completed their write. So marking an item as consumable basically means storing the write ID which we have with fetch add 1, which means the next item is going to be unique, but it's going to, if two threads are going to have some contention on that very specific line in the code, each one of them is going to get a different ID, a unique ID. And we're going to use the release memory ordering, because the reader thread would use the acquire memory ordering, which we will see in a second.
Please note that we did have some work here in order to avoid overwrite. If you remember that I said that earlier that we need to choose what to do when the queue is full, that's an example of the extra work that we need to do in order to avoid overwriting.
Right. So here's how the pipe graph of vTune for before and after we've implemented the push function. We grew from 4.4% to 13.9%. Which is also represented by that green pipe. Also note that the front-end bound had dropped from 76 to 46%, which means we spend less time in loading memory compared to what we had earlier. Some code of the pop function. So a standard pop function would generally iterate through the queues, and it would look up for the read ID item, which is known to the reader, and by the way, it's just a standard integer. Once it found it, it will pop the item, increment that ID, and return true to the caller. The top ID function basically just loads the ID, and it uses, as I said earlier, acquire memory ordering in order to do that. And pop would also either move or copy depending on the object's capabilities, and store that it is now ready to accommodate a new item. And if you notice at the last pop function, if we can go one slide back, please, the branch prediction for the read ID, or where the read ID would reside in the next time, is not very good. And if you have all the US markets in your connected to that queue, it means we will mispredict a lot. And we've tried to make something a little bit better. So we've been going to almost branchless pop, which effectively also going to go through all the queues, and instead of stopping in the middle or any branching, we calculate arithmetically the index of the queue which contains the next item. And if you take a close look, you would see that we've played with the indexes here a bit in order to make sure that index 0 represents that we didn't find any item.
So that's why we have always the index -1 when we're referring to the queue?
Right. So if we have found an item, it means we've passed to the pop line. We will pop the correct item, increment the read index, and return true.
Assaf, but here you're just always iterating through everything. Let's say that you have 100 queues. Is it still worth it? I mean, where is the balance point of this being faster than breaking whenever you find the item that you're looking for?
Right. So in order to make sure we have good figures, we've made some micro benchmarking, and it turns out that until numbers such as 10 to 15, that approach is better, and that's related to the fact that CPUs are extremely good at parallelizing operations whenever the data is available for them and whenever there are no branches, so they continue to execute parallelly, even a single core. So the improvement in the pop function is shown to be at the retargeting growth significantly to 73%. We can also see that the bad speculation is at 0%, which basically means that on peak times at least, the queues are full, which means effectively that we never go, the branch predictor would never mispredict, and we would always go to the right place.
But we still have one more branch that we'd like to get rid of. Now we have 10 minutes, so I'd like to continue with some more optimizations. So if you have any questions, let's take them offline, if it's okay with you. So we still have this one last branch. If you see it here, when the queue is empty, we have a branch, we have an if, which we don't like. What we like to do that if we look and we see that the whole queue is empty, instead of returning false, we want to continue popping, so we'll have to pop from a dummy queue. Simple. So the change that we need to implement, first of all, we install a dummy queue at the queues at index 0. This does not even have to be a real queue, we just have to expose the queue interface, pop mainly. Then we have the almost branchless pop, so queue in the index 0 is no longer invalid, so we can get rid of this if. We used to have a 0-based in queues, now would be 1-based index. So the first index would be in index 1, the second index would be in index 2, and index 0 would be the dummy. So we can get rid of those -1s. We used to always increment. If we reach here, it means that we popped a real object, so we incremented the read ID. Now we only want to increment it when we do not have, when we actually popped a real value. Similarly, here we always return true. We want to return true if we popped from a real queue. So we simply add another boolean, indicating if it's for real queue or not, and add and return accordingly. Last thing, and probably most important, we want to get rid of this comment. Another optimization, there is a change of behavior, however. Please notice that this time we do not return false and we do return sentinel, meaning we'll always update the output argument. Again, if you remember when we described the family of log-free queues, I mentioned that returning a sentinel would be faster. Another optimization that we can use is we don't want to always search the queues because we're reading an atomic variable which is slower than reading a simple int, and we have some contention. So we want to install some cache. So the reader thread will check the cache. If it's not initialized, like in this case, or if the queue was empty, it will still not contain a valid index. So if it does not contain an index, we will go to the queue, see that it's not the index that we are looking for, and just update our cache. Similarly, when we go to the next one, same thing happens. We reach the third sub-queue. We now get to the queue. We see that it is the value that we want, so we pop it and update our cache with the new top ID. So the second time that we're going, we simply check our cache. We don't need to search the shared memory. So it would be much, much faster. Here again, we reach this cell, we'll pop the item and update our cache.
Are the branches that you've added slowed us down at some level?
They may. So I think it's time to benchmark. Or maybe it's not. Remember this slide? There were 3 things that I told you to remember. That was the second one. The first one, which is the second thing that you need to remember. Always measure it in your application. If I demonstrate benchmarking here, I'll demonstrate things that we measured in our application, in our scenarios. They have absolutely nothing to do with your application and with your scenarios. I can show them what it will give you. Maybe it's good for us, but it may not be good for you. Maybe you are optimizing for something else. So do check it in your application. And when you check it, let's think about what you actually want to measure and how to aggregate the results. For example, we took a very big consideration about the utilization of the network buffer. Maybe it's not something that interests you. Maybe you're more interested in the overall latency of the event. Or maybe about the queue size. So again, measure what's interesting for you. Also about the aggregation. Because we measured the network buffer utilization, the only thing that's really important for us is the maximum utilization, because that indicates if we have drops or if we do not have drops. If we have gaps or we do not. For latency, maybe you don't care about outliers that were a bit too slow. Maybe you care about the mean or the average or the 95%, or I don't know. You need to know. You need to check what's best for you.
And our code is available. Here's the QR code of that single consumer offering. If you're interested in that, please download it, use it, experiment with it, and have fun, enjoy.
So we're almost done, but there still is the one most important thing that I would like you to remember, and that is that we are hiring. So if you found anything that we said here exciting or interested, please scan this QR code or talk to us or whatever. If you did not find it interesting and it doesn't excite you, then you probably need to think very deeply in your life. What wrong with your life that you came to a C++ conference and you don't find it very interesting? And then also send us your CV, because we're also recruiting for our full stack team, which may be more suitable for you. And with this, we are done.
Any questions?
We do have a few more minutes for questions if anyone has. Sorry?
So you kept us in tension. Did the branches on the cache slow you down?
It really depends. It really depends on the scenario. Because if your queue is almost never empty, it's different behavior than if your cache is very frequently empty. And just which optimization, the cache or the
cache with the branches.
That we added branches and we added the cache. So again, it very depends, because if you are, it depends on the utilization of the queue. Assaf, do you remember the exact numbers?
I remember it differs between different implementations, and it really depends. Yes, that's the correct answer.
Again, I was not joking when I said that do measure it in your application. An optimization that we added here could be a pessimism in your optimization. I think maybe let's something a bit simpler. Let's look at what I showed earlier about the risk check and exceptions. I don't know if you noticed, but if you use it, and even if you don't care about the exceptions, you don't measure it, but if your exceptions are frequent enough, 1 in 100, still the exception code would be slower even when the exception is not thrown. So really, when you go to this level, yes, things are more complicated than just something that I can give you a general rule. Exceptions are faster, assuming you don't care about cases when exception is thrown, and that exceptions are rare enough. So again, it's what's your scenario? Yes?
There's a well-known trade-off between performance and secure code, with secure code being the topic of lots of discussions over the last couple of years. Obviously, I assume you care mostly about performance, so how much do you still manage to keep your code secure to some extent?
When you talk about security, do you talk about cybersecurity or stability?
The things the White House mostly cares about.
Okay, so the question is the balance between performance and security. Bear in mind that our code is not accessible through anything, our application, it's only our application that runs there. No one should be able to access it, so we're not so fussy about security. Obviously, we won't leave a lot of port open and stuff like this.
Aspect as in needed to be stable. Is there some regulation over this?
There are a lot of regulations that we have to follow.
That's not in the aspect in the light of the process and its safety. That other regulations I think you refer to are related to general trading regulations, but our process might crash, and if there is a performance gain we could potentially get from that crash once in a blue moon, we are fine with that.
We can afford some risk. We do not like risks, but if we calculate, it's always a balance. I mean, we cannot check everything. So our overall focus is on performance. But I don't want to go out of here and think that our application crash every other day, right? We do care about stability because there is a very high risk for us as a company if our application will crash. Okay, so like at all times, you need to balance it. Now, we probably care more about performance than the general application, okay? But yeah, we still care about it. So to give you like percentage, I don't know how to measure. We care more about performance than the general developer or the general company, but obviously the application needs to stay alive. Yes?
You want to go back some slides?
Yeah, and you calculated with actually sequentially, or just because of slide where index plus equal.
The branchless, the first branchless version?
This one, index plus equal. So the question is, why not to unroll it? Because you can just calculate several values.
That's exactly what will get done for you in the compilation process.
And it does it better than we can.
Right?
I think we are done. Yes, we don't have more time, so. Sorry? Okay, and you're all welcome to join the meetup. It's where the food was. Most important, no? Thank you very much.
Thank you.